graphene, just graphene. Okay, so this work was funded by ANRF, DST, and a few other bunch of funding sources. So some of you know me already, and I am a thermal transport guy, but the topic doesn't directly indicate why those topics are related to heat flow. I'll try to uncover why those topics are important for heat flow in graphene. What bothers me a lot is that for a long time, people have not been able to understand how heat flows in graphene. Basically, because the experiments and theory, whatever we do to the theory, don't seem to agree with each other. So this plot here shows the first principles prediction without any adjustable parameters of the thermal conductivity of graphene as a function of temperature within this 3-phonon scattering picture. So phonons are lattice vibrations that carry heat in graphene, and the resistance to heat flow comes from scattering of phonons driven by the anharmonicity of the crystal lattice. So if you have cubic anharmonicity playing a dominant role, 3-phonon scattering resists heat flow. The quartic anharmonicity will cause 4-phonon scattering, and so on. So this prediction comes from considering only 3-phonon scattering, and you can see that the values at room temperature are exceeding 2500 watt per meter Kelvin. More recent predictions and experiment don't agree with this old result. So the red line here is this from this paper in 2023, where they have included the contributions of 4-phonon scattering to heat resistance, and they have predicted the conductivity of around 1200 to 1250 watt per meter Kelvin. The experiments consistently predict values, report values between these two limits, and these are not small differences, right? So if you take the average value here, it's around 1750. That is more than 10-20% that you associate with any experimental errors. So the experiments at room temperature and also above don't seem to match with the predictions from theory. At room temperature particularly, the values go between 1700 and 2000 at room temperature from experiments, while the most sophisticated calculations so far predict a value of 1250. So I am interested in finding out why there is a big difference in this material, while this predictive theory has worked very well for most other materials in the past, and what is the basic underlying cause. So to understand that point, we'll first have to think about what phonons are carrying heat in graphene. So in most materials, you would see in a 3-dimensional material, you would see 3 acoustic branches that are linear, but graphene is different because it's 2D. So you have 2 linear dispersive branches and 1 quadratic dispersion branch, which is called the flexural mode or the ZA phonon in the thermal transport community. So these ZA phonons are actually out of plane vibrational modes of the graphene lattice, and it turns out they carry the predominant amount of heat. They contribute the largest to conductivity. So in this plot, I am showing the value of conductivity from the ZA phonons in the bar, and the percentage is the fractional contribution to the total conductivity. So if under the 3-phonon picture, 85% of the conductivity comes from just the ZA phonons, and the percentage is not very different if you include 4-phonon scattering as well. So it's clear that we have to understand what is going on in graphene, and more, if you really have any hope of getting some agreement or explain the experiments, we really have to understand the heat carrying capability and the properties more broadly of the ZA phonon. So ZA phonons in graphene, actually I forgot to mention one thing, that in this plot, among the 73% contribution, almost all of it comes from very close to the zone center only. So the very long wavelength, small wave vector ZA phonons are contributing predominantly to heat conduction in graphene. So let us try to understand some basic properties of these long wavelength ZA phonons. So graphene is very unique for many reasons, and one of the reasons that is of interest in this context is the mirror symmetry of the graphene lattice. So this mirror symmetry is a little bit special because all the atoms lie on the mirror plane. So if you apply mirror inversion, every atom maps exactly back to itself. So this special mirror symmetry renders harmonic force constants disconnected between in plane and out of plane degrees of freedom exactly. So you can show by looking at how harmonic force constants transform under symmetry operations that the xy, the in plane coordinates, don't talk to the z coordinate. That means for any phonon, because the dynamical matrix is built from these force constants, flexural phonons are purely polarized out of plane, and the transverse and longitudinal phonons are purely polarized in plane. So how about other 2D materials? So we have shown recently that in the long wavelength limit, where most of the heat conduction happens, in many of these 2D materials, not all, but many of the 2D materials, the long wavelength ZA phonons are polarized purely out of plane. So for purely out of plane polarized ZA phonons in the long wavelength limit, we can invoke some results from the elasticity theory, because we are dealing with very small wave vectors in the elastic limit. In the elastic limit, when you have a two-dimensional membrane or a film, the bending free energy for purely out of plane vibrations has this form. So F is the free energy, H is the out of plane degree of freedom, and it only depends on H in this leading order free energy expansion. There is no in plane coordinate here. So we can show by solving the dynamical equation using this free energy that the dispersion should have an exactly quadratic relation. So omega should be proportional to q square with these constants being independent of q, and this constant k is called the bending rigidity. This is true even in elastic plates, and in the case of graphene you call this the bending rigidity to be consistent with elastic theory. And that is what we find even from first principles calculation. So these are the first principles calculations of the dispersion divided by q square. So I am trying to get this remaining factor as a function of q for different 2D materials, and you see that at small q for all of these materials the factor remains a constant independent of q. So all of these dispersions remain quadratic at small q. So when you have quadratic modes, so when you have quadratic modes, you can think of these omegas actually has the energy of excitation in the out of plane direction, purely out of plane direction. And naturally, when the energy is small, for example, for germany, a very small amount of energy is sufficient to cause large out of plane excitations, the atomic motion in the out of plane direction, and that is what we see here. So this is basically a histogram of some simulations basically using those flexural phonons, where we plot the displacement histogram as a function, displacement histogram of the displacement from the equilibrium position. In the in plane direction, because your frequencies are linear, dispersion is linear and high, the displacements are not very far away from equilibrium, but because of the low bending rigidity, the small coefficient of omega by q square, the out of plane displacements are very large. So that means the atoms are trying to move very far away from the equilibrium plane, and so you might expect that they will access the anharmonic parts of the potential much more frequently. So to address this anharmonicity induced effect of the dispersion, I have developed this self-consistent anharmonic phonon renormalization a few years back, where because of these large displacements coming in through these correlation functions, the harmonic bare force constants given by this symbol chi is renormalized into an anharmonic, a renormalized harmonic force constant. So what is happening here is that when the atoms move so far away from the equilibrium plane, they are effectively feeling a renormalized effective harmonic force constant given by this factor psi, this tensor psi, which depends on the displacement correlation. So if the displacements are 0, that is, there is no displacement from equilibrium, you recover the bare force constants. As the displacements become larger, the renormalization effect is higher, as is the case for these 2D materials in the out of plane direction. So as you can see, when you change the dispersion, when the force constants, the dispersion relations will also change, because these are just entering into the dynamical matrix, and the effect of such renormalization is very strong on a material like germany, where the bending rigidity is very low. So you can see that the ZA phonons, which are the out of plane display eigenmodes, have a large change from the bare phonons, but the acoustic in plane acoustic phonons have almost no difference in their dispersions because of the renormalization, which makes sense because the displacement in plane is very small compared to the out of plane direction. More importantly, even after including this renormalization, the dispersions at the small q continue to remain quadratic. That means I can continue to use this kind of a relation to describe these small frequency phonons, in particular with a constant factor here. So I will effectively define a temperature renormalized bending rigidity to describe these renormalized phonons. That's it. So naturally, as I kept mentioning here earlier, the lower this factor k by rho, the energy is lower. So the possibility of thermal excitation to large distances from the equilibrium plane is higher. So for germany, you would expect a larger correction due to renormalization of this factor, and for these higher bending rigidity materials like MOS2, you will expect a lower correction, and that is exactly what we see. So the top plot, the y-axis is the percentage change in the bending rigidity due to the renormalization, and you can see that for germany there is a huge effect of this renormalization. The kappa, the out of plane bending rigidity, changes by over 250% at 500 Kelvin. On the other hand, the in plane Young's modulus doesn't change much even for germany, because the in plane force constants are not renormalized as much as the out of plane direction. So this is basically describing how phonons at the small q limit change because of temperature due to anharmonicity. But these are all short range effects. So people who are familiar with DFT will know that the force constants die down to 0 with the few nearest neighbors. So these are all short range effects inducing changes in the phonon dispersion due to finite temperature displacements. But there are also some long range effects which are known to the community that change the flexural phonon dispersions in graphene, and that is related back again to this free energy form that I had showed earlier. So in this free energy expression, we have a Laplacian of H, and Laplacian is invariant to rotation of the coordinate axis. So this free energy has rotational symmetry. So now let us consider an undulation of a graphene sheet because of thermal disturbances, and these thetas are actually the angles made by the normal with the vertical direction. If I try to take a correlation function of this angle in the usual way, thermal correlation with the exponential beta f as the free energy factor, I get this expression as a result. Now this is a problematic expression because this is a Coulombic integral. So in 2D, because the Brillouin zone is 2D, d square q is just q dq times the angle. So q factors cancel and you get a logarithmic divergence with length. So what does this mean? If I try to calculate the correlation functions of normals at different points on graphene sheet, the correlation actually diverges logarithmically with length. That means we cannot have very large graphene sheets to be thermally stable. However, we know that that is not true. In reality, large samples of graphene do exist. So this is an example from 2015 where they did some exciting graphene kirigami experiments where they actually suspended 10 to 100 micron size samples of graphene and did very interesting experiments. There are some nice videos on this website as well. So we know that large graphene sheets exist. So where is the problem with whatever I presented till now? So it becomes clear if we again look at this expression. So if not to stabilize this function so that these kinds of experiments are possible, I have to stabilize this integral. So the way to do that is basically, if you think about it, if k naught here is the bending rigidity, if it is no longer a constant but has a functional dependence on q, that is if it's renormalized with respect to q, in particular with an exponent that is negative, then actually I get rid of this Coulombic divergence in the infrared. And that is exactly what happens in reality, which I will show in the next few slides. So this stability that is missing from the harmonic theory is also commonly known as the Hohenberg-Mermin-Wagner theorem for two-dimensional stability of long range two dimensional stability of ordered systems. And this is basically the same manifestation in atomic positions. What we here will show that this k naught is no longer a constant, but has to have a particular form, functional form with respect to q, with an exponent being negative. So where does this come from? Let us again go back and think about where the previous free energy expression came from first. So this is the overall free energy, including the in-plane and out-of-plane displacements for graphene. U is in-plane and H is out-of-plane degrees of freedom. So if I consider a symmetric strain tensor U in this form and ignore any out-of-plane terms here, I simply and integrate over all the U terms. So notice that if I have this strain tensor, U appears exactly quadratically throughout this expression. So I can integrate them out by using Phonon coordinates. And then the resulting F is a function of H only, which has this form. So if I use the usual statistical field representation and construct a displacement correlation function, which is the Green-Baer propagator, I get this form, which is readily integrable. And this functional form of the propagator has to be satisfied by this dispersion relation for ZA phonon. This is a standard textbook result. But in the case where the displacements are not small, as I just motivated in the out-of-plane direction, the symmetric strain also contains a term like this, which now is no longer rotational invariant. Now these contains gradient terms. Gradient terms are no longer rotational invariant. So this term breaks the rotational invariance. If I plug in this u and then again integrate out the in-plane coordinates, I end up with a free energy function of this form. This is a little bit messy, but in this paper they have developed a Green's function based framework. This looks like a Dyson's equation called the self-consistent screening approximation, where they have now calculated an effective Green's function, effective propagator, as a sum of the bare original propagator plus a self-energy correction coming from this term here. Now because I have an effective propagator, I can just use the same definition, extend the same definition and compute an effective bending rigidity, which is now dependent on q as well. So here k naught is independent of q, independent of length scale. But in this expression, now we have k dependent on q, which can be computed by just using this expression here. This is the self-consistent screening approximation. So if I do that, I actually recover very nice trends that are consistent with many of the experiments of elastic nano indentation experiments reported in the literature. So first, this is the plot of the effective renormalized bending rigidity as a function of sample size. So L is just 2 pi over q. L is the sample size and q is the wave vector of interest. When the sample size is small, you see that the bending rigidities actually just asymptotically reach the value that we had earlier, k naught. And these are consistent with small samples of graphene, experiments on small samples of graphene rotated. The red line is the graphene calculation from my work, and the black lines are the small graphene samples. And as the length increases, the sample size increases, the bending rigidity starts increasing. So it starts showing a q dependence or L dependence. And in particular, they all, for all materials, reach a universal scaling L raised to 0.82. So in this framework, minus eta is 0.82, so eta is minus 0.82. So I am reducing the power of the denominator in the previous correlation function and converging the long range correlation function, thereby stabilizing the flat face of the graphene sheet. So this result also extends to the in-plane elastic constants as well. Even the 2D Young's modulus in the in-plane direction undergoes renormalization, and that exponent has this form. So essentially, the self-consistent screening approximation recovers the universal scaling of elastic constants in the long wavelength or large sample limit. These basically are required to stabilize large samples of graphene sheet. And notice that the deviation starts happening at around 10 nanometers or so. So these are not really large. These are just reasonable samples that we often work with. And putting these two together, putting the force constant renormalization from the SCAP framework and the bending rigidity renormalization from this SCSA framework, we see that only using the SCAP framework, we retain the quadratic form of the dispersion at small q, but introduced a temperature dependent renormalization. Blue is cold, red is hot, 100 to 1000 Kelvin. Including this renormalization produces not just a change but also a change in the trend. So now K basically is Q power minus 0.82. So you have a drop in this omega by Q square as you increase Q. Yeah. So these two parts of the renormalization essentially establish how we must look at ZA phonons. So now I will come back to the original question. Is it all worth it? Will I be able to get back to the experiment by including these corrections to the ZA phonons? And in fact we do. So one of the main reasons why these corrections help in recovering experimental measurements is that we find that when we use the bare phonons given by the dotted dashed lines here, the scattering rates because of the anharmonicity of the crystal between these phonons are so high that we are actually in this limit where the scattering rates are comparable to the frequencies. So when scattering rates are comparable to the frequencies, the quasi-particles don't exist anymore. So there is a complete breakdown of the quasi-particle picture in graphene at small q when you don't renormalize using this SESA framework correcting for the stability of large graphene sheets. When I include this SESA renormalization, the scattering rates for 100 to 150 to 600 Kelvin are lying below this omega by 10 barrier. So these are all well-defined quasi-particles. So we can continue to use the Boltzmann framework to describe heat conduction through this through graphene. In fact, it turns out that this SESA renormalization, the long-range renormalization, particularly affects scattering rates among 4 phonon processes. So these black squares are the scattering rates computed with the bare force constants, and these red stars are from the SESA, and you can see that it is an order of magnitude off. The scattering rates are 10 times smaller by including this long range interaction. And the good news finally is that we are able to actually get much better agreement with a bunch of experiments from different people. So the red solid line is including the short range SCAP framework, the long range SESA framework, as well as 4 phonon scattering, and that actually matches very well, particularly beyond 350 Kelvin where the experimental error bars are smaller. On the other hand, if I use the bare phonons or do not consider 4 phonon scattering, the theory fails to predict the experimental measurements. So this kind of seems to fix the problems with the existing framework, which is particularly unique for graphene. We find that this effect is strongest for graphene and not very important for many other 2D materials. But it also has led to a very interesting foray into a new kind of heat flow regime. So till now we talked about thermal conductivity, which is in the context of Fourier's law. Heat flux is proportional to temperature gradient, and the proportionality constant is a material property called thermal conductivity. But there are many interesting non-Fourier regimes such as the hydrodynamic and the ballistic regimes where phonons can scatter but they drift without dissipating to the lattice in the case of hydrodynamic flow, or they don't scatter at all and then propagate as if they are eigenmodes in the ballistic case. So this paper with my student, we have shown that we can actually use the eigenspectrum of the phonon collision operator for 3 phonon, 4 phonon processes to find out under what conditions heat flows in these 3 different regimes. Now this is beyond the Fourier's law context. We are going to the non-Fourier regime, so we have to construct things from the Boltzmann equation, and this collision operator enters exactly in that Boltzmann equation. So for example, if you want to realize this hydrodynamic equation where phonons flow collectively undergoing momentum conserving scattering but do not dissipate to the lattice, we find that the spectrum shows that the eigenvalues are much smaller and also the contributions from individual eigenvalues are also much larger. So these 2 features are indication that the material can host hydrodynamic transport. And interestingly, we find that when we include this renormalization in graphene, it shows tremendous potential for this hydrodynamic behavior. For example, at 100 Kelvin, we see that the eigenvalues are smaller by more than a factor of 10, and the contributions from individual eigenmodes are much larger than in the case where you don't include the SESA renormalization. So in this region, you see that there are many diffuse contributions, but here that region is much smaller. So graphene actually has a huge potential to have to exhibit this hydrodynamic transport. So in summary, I hope I have shown you that the understanding of this flexural phonons in graphene is also very crucial for capturing the thermal transport experiments reported in the past 2 decades. And it has to do with the fact that there are many interesting things that happen only to graphene, but does not happen, for example, in any 3D material. All of these long range effects happen in low dimensional systems and don't affect any 3D systems. And with all these things put together, we are now able to get very good match with the reported experiments across different groups, across different time frames. So thanks for your attention. I'd be happy to take any questions.
Thank you. Questions? That's good.
Thanks for a nice talk. Thank you. One of the key things in graphene is hurdles.
Yeah.
So suppose an electron on board hurdles. So they may bring some active role.
Yeah.
Because they won't just modify the force constant, they may actively contribute. So what do you think about it?
So there are many follow-up things that we can look at. For example, there has been reports that the electrical resistivity at low temperature diverges in graphene if you have a quadratic ZF non-dispersion. Many other interesting things are there. We are systematically looking at it one by one. The first thing is that the obvious thing that I've been talking with Akshay also several times is that there are static ripples in graphene. Now these are all planar graphene calculations. So if you have a static ripple in graphene, which is most commonly occurring in many experimental measurements, how do these results change? Right? There are in all of these experiments, there are no characterizations of whether the graphene's samples were static or flat or had ripples.
And then you hold the electron put button inside.
Sure. Yeah. So
another thing I just slide
13.
I was in a sleeping mood. I thought I am looking at island, the green trees and ocean and boats.
So I can go through this again if you.
No. I'm just showing the picture. It means beautiful island. There is a slope. Please look at the picture.
Is that a compliment or?
No, the picture looks like I'm imagining.
Yeah.
Yeah. And boats, the ocean.
So actually, the colors are not just there for no reason. Like because the red region says that the quasi-particles fail because gamma is more than omega, but the blue region says that the quasi-particles are preserved. Gamma is less than. Yeah. Thank you.
Any other questions?
Yeah. Thanks. I was going to ask you that.
Which one?
I was going to ask you that ripples question. I don't know how you read my mind. So I not asked you that question. I wanted to just ask you about slide 14.
14.
So at 300 Kelvin, there's a fantastic with the theory on.
There is also a large error bar.
Yes.
Yeah. So.
Understand. Yeah. Anyways, you're getting these values which are very close. My question is, what is happening at the low temperature? At lower than 300 Kelvin, is there some other physics that is missing?
Oh no, there are no measurements that I know of at lower temperature. Like I didn't exclude it for like no reason. Okay. So there are no measurements that are reliable in the sense that they are not commonly cited in the community. I don't know of them also. Maybe I'll just add one point, right? So these effects of renormalization increase with increasing temperature. So if you get good agreement at higher temperature, you're actually at much better bet at claiming that this physics is actually happening. So even though the error bars are smaller, which is a good point, they are getting excellent agreement at higher temperature, which means these effects are actually happening in the material.
Thank you. If there are no other questions, let's thank Ravi once again.